Good afternoon, everyone, and welcome to the afternoon session. I hope you guys had a good lunch. Here we have Iddo, who's going to talk to us on reproducible ML processes with an open source stack. Iddo has a very strong software engineering, software development background. He started his career in the Army, where he served for 8 years, eventually heading the main software development school. Following his service, Iddo built technical teams for several startups in the observability, cloud, and data spaces. Prior to joining the LakeFS team, Iddo built the technical enterprise field team at Turbonomic from the ground up, as well as served as the field CTO, and was the account executive for some of the company's largest customers, up to $1.9 billion IBM acquisition in 2021. At Treeverse, the company behind LakeFS, Iddo runs all customer engagements from sales to customer success. I would like to welcome Iddo here to our stage, and please join me in welcoming him.
Thank you. Meaningless introduction, by the way. Let me introduce myself in the right way. I'm Iddo. I'm from New York. I have 3 perfect daughters back home, and I'm here with LakeFS. My background is in software engineering and data, and I'm new to data. I've actually been in data for like 2-3 years with LakeFS. Before that, I was in many other software aspects. So maybe we can share that. So it's always fun after lunch. Everybody's very up and aware. So I guess just a question of the folks that are here. Any data scientist? Okay, any data engineers? Okay, ML ops, data ops, data analyst? Okay, great. So that's usually what happens, right? There's a lot of everything. And today we're going to talk about building reproducible ML processes with an open source stack. Like as I mentioned before, I'm new to data, right? So this has been the first time for me over the last 2-3 years. Before that, I spent more traditional like cloud, enterprise software, things like that. And my first impression when I got to the world of data was, what the? And the reason is because there is just like this unbelievable amount of moving parts in the data stack. It is insane, right? So if we think about just a very small partial list of available just open source, right? I'm really minimizing this. Softwares that a data scientist and a data engineer will work with for ML. We start with the programming languages, right? Python, which I think is probably the elephant in the room at this point. TensorFlow, PyTorch, Pandas. I'm not going to go and explain each one of those, but I'm assuming that a bunch of you are using these today. And then on top of that, we have everything around handling and processing the pipelines, the compute systems, the Sparks of the world, right? Either open source or Databricks and so on and so forth. And then you have everything that managed the models, right? The MLFlows in the world, which just helps you manage your experimentations, which you have many of those. And then you have your notebooks, and those are a little bit different, right? So you can have your Jupyter notebook or your Google Colab or whatever it is that you use today. And then you also have data version control systems. Now, in case it's not clear, I'm very biased, right? I work for LakeFS, right? I contribute to the LakeFS code. LakeFS plays in this space of the data version control system, and I'm obviously going to focus on that. But the demos that I'm going to give here, including links and barcodes, are demos for a complete open source stack, including more, by the way, like Min.io as an object storage below it, which is also open source, those of you familiar with. And it's going to have Python and PyTorch and Spark and MLFlow and Jupyter and LakeFS. And I'm going to give you a link, and you can download that link, and you can bring all of that together, and you can play with everything as you wanted. But of course, in this call, I will kind of focus on LakeFS. Just a little bit about the company, just so you know. We started 4 years ago, built this solution. Dr. Rinat Or and Oz Katz, both like CTOs, head of R&Ds in very heavy data companies that kind of figure out that you have the data engineering side, the software engineering side of the house that's very, very organized, right? Any people with data engineering backgrounds? Okay, very few, okay. Everyone works with Git. There is no exception. Everybody versions anything. It doesn't work otherwise. And then you have the data space, which is new. How many folks here have been in their current role of that data engineer, data science, whatever it is that you do, not company, current work, the current job, more than 2 years? More than 5 years? Yeah. We're all figuring this out. So that's what happened. There's a lot of room for putting processes in place. At 2022, we launched LakeFS Cloud. At 2023, we launched LakeFS Cloud, LakeFS Enterprise, which are have additional features on top of the open source. I will focus on the open source in this talk. So I'm not focusing on the paid features and the differentiations. And it worked out, to be fair. We have thousands of organizations that we are aware of that are using our product, which I'm very happy about. If you go and you log into our Slack and you connect there, you will literally see all of these and many, many, many more, right? Thousands of people that are there. Some of the people that are here are customers. As you can see, like we play in big data, right? ARM, Toyota, NASA, we play in big data, right? We're talking about data lakes with hundreds of petabytes of lakes for some of our users. And this is what we do. We sit on top of an object store, and that object store can be a cloud object store like Azure Blob Storage, AWS S3, Google Cloud Storage, but it can also be an on-prem object store like Min.io, Dell ECS, NetApp Storage Grid, Pure has, I forgot what they call it, there's literally dozens out there, right? And imagine that you can take a bucket and you can give it a Git interface, right? So you can now take your data and you can branch it and create a copy of your data. And then you can make changes into that data and you can commit those changes. If you wanted to, you can roll back changes. You can make many changes and then merge data and promote data like you will promote code, right? So I made all these changes, I'm happy with them, I'm gonna merge that back in, like a pull request, if some of you are familiar with. And then the ecosystem of tools, and God knows there's a lot that you run, can access the data through the LakeFS API and get those versioning capabilities with very, very minimal refactoring, up to no refactoring, which I'll talk about in the end, right? So if before I was accessing a collection on a bucket, now I will access a name of a branch or a commit identifier. What's a branch? A branch is prod test dev, or experiment 5, 6, 7, experiment 8, experiment 9. All of these can be branches. We literally have users with millions of branches. Everything that we do is in big data numbers. Okay, this is not meant for small data scales. That's, I will say, the biggest differentiator between us and everybody else. Now, a commit identifier will be something logical. For example, the set of raw data, processed data, and final data that was used to train a specific model at a specific time. That commit, that point, right? Or from a data engineering perspective, all the changes that were made as a part of an ETL. What the data looked like at the end of the ETL, what the data looked like at the beginning of ETL. And not from a time travel perspective, but from a logical perspective, right? Just the things that changed the part of this ETL. If you think of code and Git, other things might change in the same time also. But this is the logical change that I'm referring to, right? And then all those Git actions, you can run them in many different ways. You can run them through a command line interface. As you can see here, lakectl create branch, right? Or lakectl commit. Or you can run them from Python code inside your notebook, which I think is very common for data scientists. You can run them from a DAG, an Airflow DAG, from a web interface, right? Or you can actually take a repository and mount it to your local file system and be completely oblivious to the fact that something is versioning it, right? And everything will happen magically in the background. So how does it work? So I mentioned before a couple of times object stores. The reason that we support object stores is that we take advantage of a very specific property, which is the immutable nature of the object stores. Every commit in LakeFS is basically a collection of pointers to files that sit on top of your managed bucket. Now, I'm going to say this twice, and that's not enough. All the data always sits by you. We are not a storage solution. I do not sell storage. Even if you ask me to, I have nothing to sell, right? Ever. I do not sell storage. All the data, all the metadata sits by you. And I think that's a big reason why we have those thousands and thousands of users, because data, in case you didn't notice, is sensitive, right? And not everybody wants to share it with the world all the time. So all the data and metadata sits by you. We just have pointers to those data. We don't even need permissions to read and write the files, by the way, because I don't care what's inside of them. I'm completely format agnostic. I just need to know what the metadata of the file is so I can version it. So we actually version data that we don't have permissions to read and write. Now, the object store is immutable, so if I go and I change a file, what actually happens is a new version of this file is being written to that object store. And then we take advantage of that and we do copy and write. So the next committal point in LakeFS will point to that additional file. But files that did not change, like the 3 files on the top, you will have multiple commits pointing to the same physical objects. And the reason that is very powerful is because if I want to create a branch of 200 petabytes right now, that's a metadata-only operation that will take a millisecond. It will take a millisecond for a gig. It will take a millisecond for a petabyte. It will take a millisecond because I'm not actually copying the data, right? I'm just creating more pointers. And then that branch can work in isolation and do copy and write on their changes. And you get that lineage over the tree over time. And a lot of time in these data lakes environment, most of the files are static, and then a smaller subset of the files changes on a regular basis. So you actually get like a deduplication of the lake over time. You can go back in time without taking snapshots of the same files over and over and over again. So that's how we work with any format, completely format agnostic. This can be Parquet files. This can be iceberg tables. This can be Delta tables. We work with the world's largest I would say iceberg user in the world. We are partners with Databricks, who are the owners of the developers of Delta tables. And we work with images and videos, right? Any table from any format whatsoever. And the use cases for this are a few use cases. Today, soon, I'm sure that we have 17 minutes, right? We're going to speak about machine learning data reproducibility, which is the ability to understand what was the data that was used to train every model. But there's other use cases to this, and this is also worth mentioning, right? Just the fact that I can run experiments in parallel with the same data by creating multiple steps, right? If I don't have to copy the data locally, that means that I can run many, many experiments and use the cloud scale in order to do that. I can prepare my data in isolation, so I'm not going to step on anybody's toes. Right? I'll create my own copy of the data, which honestly is what happens today also, but I'll do that without copying anything, and I can work in isolation. And we also have some advanced features which I'll barely speak about today, like metadata search, like give me all the PII data from my data, now that I have this, or the ability to get very, very quick loading time for loading time for deep learning scenarios by actually mounting a repository on top of your operating system. So here's the day in the life of today. You have data in many places. Tell me if this sounds familiar. What's the first thing that you need to do when you start to work on a data set? You copy some data. Not all the data, some data, right? You sample some of the data, then you train your model, you create a model, and then you version that model. Now, version, that's a bold statement when I say version the model, because maybe. we use experimentation management. What we typically version today is like the experiment categories, right? Like how many epochs, what optimizer did I use, things like that, right? Not necessarily the data. I don't necessarily version the data that I use to train this model, and this is where LakeFS comes into place. And then you wait for this to finish, and then you do this again and again. Sounds familiar? Like, yeah, no? Yeah, okay, good. I'm happy that it sounds familiar. I'm not aware. I shouldn't leave the room. Okay, good. Now, with LakeFS, you can continue working the same exact way. if you want to. You can continue doing the same thing and just achieve data version control as well with working locally with your data. So if you wanted to do this, we have a way to work with the data locally. So you can run a command line that will do a local clone of your environment. This is kind of similar to, did anybody here use DVC in the past? Yeah, so this is the DVC approach, which is also available in LakeFS. You say, oh, you know what, give me a version of my data, and then we will go and we'll get that commit identifier. You will copy everything locally to your environment, and if you edit the file and change it, once you commit, we'll go and we'll point to that next file, and we'll do all of that. So this is, those of you who are familiar, this is the DVC approach to work with LakeFS. You can continue working the same way, should you want to. And if anybody wants that sample, start to finish, the entire thing, all the code prepackaged in a single Docker environment, go ahead and take a picture of that. You can clone this repository, run it step by step, and it will give you the entire thing from start to finish. I actually am using this because yesterday, I don't know if it's going to be available or not, but yesterday we had like an hour-and-a-half workshop where we did this. My colleague Amit, who's much smarter than me, did this step by step and walked everyone through it. But this is the tutorial. Now, but there is a day in the better life of a data engineer, which is not working locally with the data. Stop copying the data locally at all. Like, don't do it anymore, right? Which is, instead of running things on your local machine, take advantage of the cloud, take advantage of the GPUs on the cloud, and work with a notebook remotely against the data sets, and just train everything on the cloud. So you work with the data staying in place without that Git local thing, right? Just directly in front of the data lake. And then you can run this without waiting. You can run 1,000 of those in parallel, because you don't have to copy data all the time. Now, I mean, I obviously I didn't develop anything in order to be able to do this. The only thing is that if you don't need to work locally, if your versioning system can work with the data staying in place, now you can do this using, I don't know, Spark ML, for example, if you wanted to. Now, if anybody wants to do that, there's also a step-by-step example for that you can use. So I have that available here also. It's actually super, super nice. It's a Docker Compose that will spin up for you LakeFS, MinIO, Jupyter Notebooks, MLFlow, the entire thing, and you can work on it together. So it's pretty powerful and a great way to learn. That's one of the advantages of the open source project, which is you can just go ahead and text it. And the disadvantage for someone on the commercial side like me is I'll never know that you did it. Okay, so that's great for you. We do have a few. I won't be doing my job unless I say we do have. Okay, first of all, everything that I showed you up to now, 100% of it is open source LakeFS. Okay, that's worth mentioning. So, and it forever will be. Okay, all the core versioning of LakeFS, that's our commitment to the open source. All the core versioning capabilities of LakeFS are open source, and they will remain open source over time. Right? And then on top of that, we have a hosted solution, LakeFS Cloud, and an enterprise solution, which is you host LakeFS, the LakeFS compute side on your VPC or on your data center if you have one, right? And we version the data for you in both cases. In all cases, like I mentioned before, I promise one more time, the data sits by you. We never store any data or any metadata. We are not a storage solution. But we do give enterprise features on top of it. So if you need RBAC, SSO, SCIM, auditing, mirroring, all those advanced use cases, you can use LakeFS Cloud or LakeFS Enterprise. Now, because I don't know if you noticed, but there is practically no internet here. So my demo is actually a screen click that I went through. I apologize for that, but that's what I can do without a demo. What we see here is the ability to go to an MLFlow and basically from MLFlow, go and link into LakeFS and see a specific experiment. So from MLFlow, I went to LakeFS to a specific commit in a specific repository. And here I see the gold data set that was used to train a specific model. But I can also go to the raw data set. Because it's a commit step, I can go all the way back to the raw image files that we use to train a specific model and go back from there. So that's super powerful, right? So imagine that you can go to each experiment and see the entire flow of the data from raw, cured, this is starting with the experiment itself and going further. So it's also the world's fastest because it's a screen share, but this is one. The other thing that we recently came up with is actually a way to completely take out the interface. So we found out that a lot of data scientists would rather not work with any interface. Like, I don't want to work with any Git. I don't want to work with any data, LakeFS local. I just want the data to magically appear in my environment. And so that's what we did. So I have here a repository that has 27,000 files, 3 terabytes of files. Okay? Not that bad, not bad. So what I can go is I can go to my terminal, and I can run a command called mount, or Everest. Everest mount, I think, pun intended. And then I can take this data set with 27,000 files, and I can mount it locally. I forgot the space here. I can mount it locally together with my environment on a directory. Now, as you can imagine, when I did this, I didn't actually copy 27,000 files. Right? This is not the time that it takes to copy 27,000 files. But I do have the data sets now, and if I check, I will see that this is mounted to 127,001, and it's using 0% of my storage. And the file is here running on a local mount server that is running on my environment. But I can go to these data sets, like the book data set that has some Parquet files, and I can use DuckDB, for example, to query some of this data. Now notice that the first time that I'm going to run this command, it's going to take a second. Because the first time that I'm accessing these files, I'm actually getting the files from the object store to my local environment. The second time that I run it, it will be immediate, because it's cached, right? So I start a mount that gets all the metadata files, all the metadata of the files. I have all the files here, and when I start working with them, then they come to my local machine, and they stay there. And that's very powerful also for deep learning, because what happens, you guys know this better than me, is that you end up accessing the same files over and over and over again, and that's very powerful. There were some comparisons here that I saw about response times, and this will increase the response time of LakeFS by orders of magnitude for someone that's using deep learning. I think there was a question.
Is there like an extension that you have to load in DuckDB to connect to LakeFS?
No.
It just works. It's a file.
It just works. LakeFS. So first of all, LakeFS itself, just so you know, has DuckDB inside of it already. So when you go and you look at the LakeFS UI and you see some Parquet files, there's a built-in DuckDB that you can go and you can query your files. That's one. Secondly, this is a file system. You don't see. This is, like, you don't see, like, as far as you know, this is just your files.
I could open it in another program. Or
You can open it in any program, and you can work completely oblivious to you. And look, many of our, like, we have a lot of Databricks customers. We have a lot of, like, there's a few ways to interact with LakeFS. Mount is one of them. Python code we spoke up. We spoke about. We have, like, when you want to load the data, for example, with Spark, you can use a gateway. Like, we have a generic S3A gateway that basically catches every type of gateway-compatible solution. You can always go with it. And we also have specific clients. So we have a Spark Hadoop client, for example. And one of the main advantages of those, again, for performance perspective, is imagine that you're running a Spark job, and you want to get your data. So you go and you ask LakeFS for the metadata. LakeFS returns the metadata, and then the data flows directly from the storage to the compute cluster. And we're not in the way, right? That has a lot of implementations on performance and security. And there's multiple clients as well that we can work with. Any other questions, if we already started? OK, fantastic. So just a few takeaways. We have an awesome Slack community, right? We have thousands of people on it. I hope this barcode works. Someone can tell me soon. But this is basically a link to our Slack community. It's a great place to learn about LakeFS. Again, one of the advantages of open source is It's very, very battle tested, but there's also a bunch of people to ask questions and get to learn a little bit more on the project. So I will encourage anybody that wants to try this out to do that. To run LakeFS in your environment and try this out, you need to run a single Docker command. Right? So anyone that can run Docker can try this out on their own. So with the demos going a little bit, oh, wait, this is also very important. This may be the most important. This creature that you see here, this over here, this is Lottie. Lottie is an axolotl. Those of you who are not familiar, this is the creature that lives in lakes in Mexico specifically. And just like us, we live in lakes and we help keep it clean. And that's why that's our mascot. We have some socks in the booth. When I say some, I think I have 3 left. So, so those of you who are interested, come back and come by and pick them up. Any questions?
What's the compute requirement running locally?
What's the question was, what's the yeah, so we have a really pretty big sizing document that you can see on docs.lakefs.io. But to give you like a role, it's very small. What very small I mean? The other day I was on a call with a major space agency, okay, that tried LakeFS and did the entire performance testing on a local Docker on someone's laptop, and it worked. Okay, so we have a pretty good. I mean, this is planned to work with millions, if not billions, of objects, and it's a relatively small footprint. You can, and again, it's all very, very well documented at docs.lakefs.io. If you look to understanding LakeFS sizing benchmarks together with benchmarks, and it will give that information.
Does it support merging data like Git?
Absolutely, that's a fantastic question. Yes, it supports merging, and to kind of expect the next question, and we have a merging conflict and handling as well. And that's a huge use case. So that's on the data engineering side, very common. So almost all our users, what they do is every time they run an ETL, some sort of transformation, they'll take the data, they'll branch it out, and they'll make changes, and you'll commit as you go. And at the end, you will merge the data back into prod. What this gives you is this. If the ETL fails midway, nothing happened to prod, right? 2, at the point of the merge, you can run Git actions, automatic data quality checks, like the schema didn't change, I don't have PII data, or complete business logic. Unlike Git, by the way, we are not running Git in the background. We give a Git interface, Git does not scale. Any other thing that runs Git will eventually not scale. So we're not running it, and you can, unlike Git, you can actually access at the same time different branches. So we have one user who's like a delivery service. And what they do is when they run the ETL, before they promote the data, they see that the total number of dollars met from all order didn't change because it shouldn't change as a part of the ETL. And if it changed, that's an indication that something was wrong. Right? So they check what was the dollar before, what was it now, and only if it's so, they approve the merge of the data, right? You can promote the data. And the third thing that it gives you is, even if you completely messed up and you didn't find out and you find that out that there's a problem after the fact, those of you who have been working on a data lake know that rollback is a manual, heavy lifting, labor-intensive, time-consuming headache to try and recover, even if you have like the time travel on a specific table. And if you have unstructured data, you're completely lost. That's a good word. You're completely lost. So then this allows you to recover very easy. So those are the 3 things that you get just from the merge. Yes, sir? Oh, that's a fantastic question. We don't transfer data. Because even though the data sits by you, I actually don't transfer the data. I use pre-signed URLs. I give you a pre-signed URL, and then within your cloud, you will get the data from your storage. So, which is also a security benefit as well. I don't need to be on the same VPC. You can, by the way, you can if you wanted to, but regardless, I don't, like, you have your compute and your storage, which I have nothing to do with. My compute just does the versioning. You will ask me just for the metadata is very small. Okay? You will ask me just for the metadata, and then you will go and you will, within your VPC, just like you do today, get the data itself. You only get the metadata from me.
So, pre-sign URLs, you're fetching the data from the data center, I mean the cloud provider, right? Does it,
I don't actually fetch it. I just give you a pre-signed URL so you can fetch it.
but somebody is paying, right?
Yeah, you will fetch it with your compute and your storage.
Okay.
Yeah. So you have your compute, your storage in one VPC. My compute, if you want, if you use LakeFS Cloud, and a different VPC if you use LakeFS Enterprise or LakeFS Open Source also within your VPC. But regardless, since the data doesn't flow through LakeFS ever, then there's no egress cost associated with it. I mean, there's very minimal, right? The whatever, sense, right? Oh, am I over time? Oh, I'm over time.
Sorry.
Thank you so much. Thank you, appreciate it.
Thank you.